Okay, I want to point out that shear stresses are generated in the soil as the wall moves out. So how does that occur? Well, here's my wall, and the wall is moving in this direction, and if I'm looking at this wedge of soil here, what happens to it? Well, the wall moves to this location, and we get a wedge of soil that moves toward the wall. This soil doesn't move at all. There's going to be some soil that doesn't move when the wall moves, but some of the soil does move. So what we find is that there's a shear plane right there. As that wedge, one way to look at it, wedge moves, it doesn't move as an entire block, but sort of, as that wedge, basically slides along this plane toward the wall to stay in contact with the wall. In other words, we don't get a gap there. So we get a shear plane. And when we have a shear plane, meaning it's failure, a shear failure, then that's why we use our shear envelope. Our Moore envelope helps us predict these stresses because we are getting a shear plane. And so we're generating shear stresses in here, which means that we have to be concerned about drained and undrained situations. And so, well, we're getting a better understanding of the process, and therefore we can refine our calculations a little bit more than we did last semester. And I'll just point out that later on we're going to analyze this wedge here. If I look at that wedge, I have the weight of the wedge. And when we've made a cut, so I made a cut there, I made a cut of the wall, and so I'm making these cuts, and with soils, whenever we make a cut, we have a normal and a shear. So I make a cut here, I put a normal and a shear. I make a cut here, I put a normal and a shear. So we can analyze this wedge here, and if we figure out those forces, well, what are those forces? These are the forces that the wall applies to the wedge in our free body diagram. So in other words, the wall applies these forces to the soil, which means that the soil applies those same forces to the wall. So these are the wall forces. So certain situations we can use this analysis technique to get the forces on our wall. So we'll do that a little bit later. And it's similar to what we're talking about with say I have a slope here, and I have soil on top of rock, so rock down here, soil on top of the rock, common situation. I can analyze this wedge here, and I analyze that wedge in the way that we have looked at it in your statics class, basically, where we have a weight and we have normal and shear on our soil. And, the geometry can be a bit different, could look something like that. And then I'll note that, remember, we don't, in the design of our walls, we don't want water piling up behind the wall. And so we put drains. Now, this is not a realistic wall, but we want to make sure that the face of our wall allows water to seep through it, with drain holes at certain locations, so that we don't get water piling up behind the wall. Because if we get water piling up behind the wall, we're increasing our forces on the wall quite a bit. So we don't want that to occur. I'll do that later. Okay, so we need to, because of these shear stresses, we need to analyze the clay drain situation, and we will analyze the clay undrained situation. And if you remember I asked you to memorize the different failure envelopes. So we've already analyzed this one, that's sand drained, where the failure envelope goes through the origin, and we have our angle phi prime. Well, clay drained, what? For clay drained, we have our failure envelope. It does not go through the origin. It has a C prime and a phi prime. And then when we do clay undrained, we have the angle is 0, and we have the intercept is SU, or sometimes called C. So we need to keep in mind these 3 failure envelopes. They're key to us for the rest of the semester. Actually, you need to be aware of those 3 failure envelopes. So know those. And right now we're going to do clay drained, which is this envelope here. And what do we get? We're going to do the same thing. I'm not going to go through all the geometry this time, but we have a circle that is tangent to the envelope. And, for the active situation, we have a bigger sigma v prime than a sigma h prime. And when I do this geometry, I'm not going to go through it. I end up with this expression. So what is it? Sigma h prime, so this is my sigma h prime, is equal to sigma v prime tangent squared 45 minus phi prime over 2. Well, that's the same. That's what we had. That was, Ka for our sand. So if you've already you should have already memorized that. Tangent squared of 45 minus phi prime over 2. So this portion of the equation for sigma h prime is identical to sand. But then I have this c prime, and that changes my equation a little bit. And it goes minus 2c prime tangent 45 minus phi prime over 2. So notice this one is tangent squared. This is just tangent. So it's easy to remember. You've got 45 minus phi prime over 2, and it's either tangent squared or tangent. And then you just have to, the only hard part here is the minus 2c prime. But I want you to memorize that expression. For the passive side, passive is what? It's really this, it's this circle out here where, out here I'm at sigma h prime. In other words, the sigma h prime is larger than the sigma v prime. That's in the passive region. And if I did the geometry there, I would end up with this expression, which is, again, I see tangent squared of 45 plus phi prime over 2, same as the Ka. So in other words, this is my Kp for sand. So that is the same. And then it's what? It's plus 2c prime tangent 45 plus phi prime over 2. So notice this expression and this expression are identical, except for minus signs in the active are plus signs in the passive. So if you memorize one, you're set. One of them has all plus, the other one has all minus. Other than that, they're the same. And I'd like you to memorize both of these. So, but if you memorize that and that's the K and Kp for sand, so you need to memorize those. Then just put on the 2c tangent 45 minus phi prime over 2, or tangent 45 plus phi prime over 2. So easy to memorize those. All right, so what is my lesson here? Well, my lesson is that when I have sand and gravel, my sigma h prime is very simple, Ka sigma v prime in the active, Kp sigma v prime for the passive. So that fits exactly what we've always done. Now we're making it a little more complicated because now I can't do this for clay and silt. I cannot do this simple. We have a big does not equal sign here. It's more complicated, but not much more complicated. I now have to put in this 2c prime tangent angle thing. So the lesson is for clay and silt, it's more complicated than just Ka or Kp. I have to put in this 2c prime thing, use the formula shown. So a little bit of a lesson there. Okay, now let's do clay undrained. And then we're plotting total stresses. So remember, we have our Ed's tough, and we're here, total undrained fast, because we're doing clay undrained. So what are we? Total undrained fast, which means we're using total stresses. So we're using our envelope, and if you remember our envelope that has SU and horizontal, which we just went through, it is with the x-axis is total stresses, So now the geometry is real simple because I'm going to end up again with an active and passive. So if I have a sigma v here, now when the wall moves out in my active zone, well, things move in that direction and I get a point there. So there's my active circle, the circle that I would get under active conditions. And then I get that circle for the passive conditions. So the horizontal stress is increasing. And assuming I know what SU is, then my sigma H active, undrained, is simply sigma V minus 2SU. Why? Because the radius of the circle is clearly SU, then the diameter is 2SU. So here's my sigma V. The diameter is 2SU, so it's sigma V minus 2SU to get to sigma H active. And then, of course, for passive, I simply add 2SU. So it ends up to be that sigma H passive undrained is sigma V plus 2SU. So once more, I'd like you to memorize those two to get the active and passive. So it goes back to what we just said, which is, again, well, I could add on here for clay and silt is that it's more complicated. In other words, I don't use my Ka and Kp for clay undrained because here's my new equation, a little bit different than what we had before. So, all right. Let me go through a little example of what we're talking about to a certain extent. Suppose I have, so this is my clay undrained situation. And I'm first going to tell you it's simple, but everybody uses this little example. Suppose I have a clay here. I've got my wall, it's 2 meters high. And there's my water table. But this is clay undrained, okay? And my undrained strength is 20 kilopascals. My gamma saturated is 20 kilonewtons per cubic meter. And I want to find the wall stresses, and I'm just going to do it undrained. Well, that means what? Then I use these, well, there's no passive there, so we're just going to use the active. So all I need to do is use the active, because this is the active zone. There's nothing in the passive zone. So I'm going to use this expression, sigma V minus 2SU. All right, so we set up our little table, and our table now is a little bit simplified because notice everything is total stresses. Why? Because it's total undrained fast. This is total stress, total stress, total stress. Everything's total stresses, which means that when I make my table, I can skip some columns here. So I simply have, depth sigma v and sigma h. That's it. Very simple. So a depth of 0, I've got 0 there, but this is what? 0 minus, remember it's minus 2SU, minus 2 times 20, I get negative 40. That's interesting. Let's see what that means. And then at 2 meters, well, my sigma v is 2 times 20, so I get 40 minus 2SU. The SU is given as 20, so I end up with 0. Okay, so what does that mean in terms of our stresses? So, well, in a nutshell, in soils we don't like these negative stresses, because in this particular case we have a negative stress at the ground surface. It's going to separate. Soils generally don't take negative stresses, and so that means that I would get a crack here at the top of the wall, or not there, over in here, as the wall moves out in that direction. Negative means tension. In geotechnical engineering, negative is tension. In structural engineering, negative is compression. But in geotechnical engineering, negative is tension. So we would get some separation there at that top of the wall, and then down here we have 0 stress. So if we look at this, what do I have? I have a wall that has no stress on it. So I figured out the stresses on my wall is 0, because I get cracking at the top and then it becomes 0 at the bottom. But and so it comes down to, if I have a wall with no stresses on it, do I need the wall? The answer is no, I don't need the wall. So what we found is what is called we have calculated the possible unsupported height of our clay. All right. So in other words, given these particular properties, I could make a cut in this clay, and I don't need a wall. I don't need a wall. So what does that mean? That means that if we calculate our vertical stress as being gamma saturated times Z naught. I'm going to use Z naught as our unsupported height. Well, let's just use Z naught is the depth of our interest, depth of the point of our interest. If that is the case, then, and we have sigma v minus 2SU equals 0. So in other words, that's the cut. When sigma v minus 2SU is 0, that is the depth at which the stresses are 0. In other words, they're no longer negative. They are now 0, which is what happened when we got this value right here. What was it? This is my sigma v minus 2SU. It came out to be 0. Well, so if there's 0, if my sigma h is 0, so there's my sigma h. When my sigma h is 0, then I don't need the wall. And when at that point that is 0, then that means that above that it's negative, and below that it's positive. So that gives me our depth at which we don't need a wall anymore. So in other words, if I can figure this out, when that is true, that is the depth that a wall is not needed. So that means so this is that equation that we just did, and if our sigma v is gamma saturated times the depth, then gamma saturated times Z naught minus 2SU equals 0. I can solve that expression for Z naught, and we call that the unsupported height. In other words, 2SU over gamma saturated gives me my unsupported height, which is a little bit handy if I know the undrained strength of our clay. I can just do this little simple calculation and get an estimate of the unsupported height. Now, this is a temporary thing, and you don't put people down into a trench at that unsupported height and that sort of thing. So don't go overboard with this expression when you're working in the field. Like I say, it's temporary because climatic conditions change and things like that. We don't want to put people into a trench unsupported. So this is just an estimate that people use for a temporary trench, for instance, that you could dig. I give you an idea of how deep you can dig without supporting something for a temporary basis. Okay, so let's take a look at. Now, let me make one other comment here. This one reason this is simple is what? Is that I gave you an SU for all of this clay. Well, we know that SU varies with depth. So that's another problem with this little expression that I just developed, in that, SU varies with depth. So this SU is sort of an average over this 2 meters, is the intention of that, and like I say, so this is not a perfect equation or anything like that. But all right, let's do a more formal analysis. Let's suppose we have this situation whereby I'm going to say that this wall is built. Now we're going to take into the way the wall is constructed is going to influence our pressures on the wall. We're going to find out. So adding some more complications here as we go along. Now, so I have sand over clay. I've got a water table here, and 6 feet. We got an anchor at 2 feet. Wall goes down to 12 feet. These are our soil properties. Now notice what I'm giving you. We've got our C prime, our phi prime, and I have our SU over sigma prime I. I haven't given you a Ka or Kp. Now you need to determine what those are, in essence, and what the stresses are going to be. So find the active and passive stresses at t equals 0 plus. So in other words, and I say that it's built by excavation. So what we're looking at is, so what is the solution? What does that mean? I built the wall by excavation. In other words, we drove, for instance, a sheet pile wall into our soil, and what we're going to do is excavate this side. So this is my t equals 0 minus situation. And then my t equals 0 plus, we're going to assume that we excavated all of this and put in our anchor instantaneously. And we want to know what are the active and passive stresses at this particular time. So t equals 0 plus. How do we look at that? Well, we look at it in the way that we normally do things. And what depths are we interested in? Well, start there. Well, our anchor's at 2 feet, so we're at 2, and then I have a boundary at 6, so I have a 6 minus and a 6 plus, and then my 12. And over here I've got a 6 and a 12. So those are my depths that I'm interested in. And I start with the sigma v's. Well, I'm not going to go over all of those, but at those depths, you can figure the sand is dry, so this is just 2 times 100, 6 times 100. That's the same. And then I have my 6 times 100 plus 6 times 110 at 12. That gives me 1260. On the other side, in the passive zone, I've got 6 times 110. So we have those. Now, notice we come up with U. Now, this is where we have to think it through a little bit, but we're always doing our EDS tough situation. And what do we find? We're at t equals 0 plus. Well, what is that? That is our undrained situation, right? No time has passed. So total undrained fast in the clay. But the sand is always effective drain slow because it's, first of all, because it dissipates excess pore pressures instantaneously is what we envision it. And so we have, so this is in our sand, we're effective drain slow, but in the clay, we're our total undrained fast. So that's what happens at our t equals 0 plus situation. The clays are going to be total undrained fast, the sands are going to be effective drain slow. It's always going to be that way at t equals 0 plus. So when I do my sand, I'm worried about effective stresses. I got my U, I got my sigma V prime. Now, of course, the sand is dry, but no matter, that's the way we're supposed to do it. We got to put in our U equals 0 and get our sigma V prime. And then our sigma H prime for the sand is simply the Ka, which, I didn't make a big deal about, but what do? I gave you the phi prime for the sand, so the phi prime was 33 degrees. So tangent squared 45 minus phi prime over 2. I plug that in, I get my Ka is 0.238. So I put in Ka sigma V prime here. And then I add the U, which is 0, so I get my 48 plus 0 is 48, 143 plus 0 is 143. So I've got my sigma H here. But for the clay, so now I'm in the clay region on both sides. Well, what's the expression that I need to use? I'm using clay undrained, and the expression is sigma H is equal to, the sigma H is sigma V plus or minus 2SU in the clay. It's sigma V minus 2SU for active, sigma V plus 2SU for passive. So sigma V minus 2SU. Sigma V minus 2SU. So those give me my sigma H's in the clay. Over here it's sigma V, but now it's plus 2SU. And so I get these sigma H's in the clay. Now, I guess for the clay, we also needed to get our SU, which I skipped over, basically. And because we were given our SU over sigma prime I was equal to 0.4. That was the given information. And so, let's just go back. SU over sigma prime I was 0.4. Given that, so I get my sigma V prime in my clay at the various depths, and I multiply by 0.4, and so I get my SU at the depth of 6 and depth of 12. Now, I have to look at my picture at t equals 0 minus. This is an important point. When I get my SU value, I have to look at my t equals 0 minus picture. So, in other words, we built the wall by excavation. Well, that means what? My t equals 0 minus looks like this. Doesn't look like this. It's not that. So I have to use my t equals 0 minus picture, which means that the weight of this sand influences the stress in that clay. we're assuming that this sand has been on this clay for 100,000 years or whatever, how long that sand has been there, and it's influenced the strength of this clay. So I look at my t equals 0 minus picture. I get my sigma v prime, and then SU over sigma prime I. Well, sigma prime I is my sigma v prime at t equals 0 minus. So that's equal to 0.4. So to get my SU, I'd simply multiply 0.4 times sigma v prime. So I'm using that SU. So these SUs, I have an SU at 6 of 240. So there's the 240 there. And there's the 240 there. Those were both at 6. At 12, I have 354, so I have the 354 there. So I use this equation here, but I have to make sure I use the right SU. And then these are the stresses on my wall. So plot these stresses, those are the ones. In contrast, we can create a wall by filling, not excavating. How do we do that? Well, here's my t equals 0 minus situation. For instance, I have clay here, and I have my wall sticking up out of the ground. And then what do? I fill this side, so I put it, there's my sand fill. I have my anchor, and I have the same depths, 0, 6, and 12. So interestingly enough, it's the end picture is the same. So in other words, if I look at this picture at t equals 0 plus, I've got what? 6 feet of sand, 6 feet of clay, basically. Compare now, which is what we had before also. 6 feet of sand, 6 feet of clay. So I have the same result. The end product is the same, but I built the wall in two different ways. For this one, I excavated one side of the wall. The other one, I filled one side of the wall. And what we're going to find is we're going to get different answers for the stresses on the wall because of the way that we filled it. So this is a complication we did not take into account last semester. And what happens is my table for my SU is now changing because I have to use my t equals 0 minus situation. T equals 0 minus situation this time is like this. There's no sand here. There's nothing there. So that sand has not consolidated that clay and strengthened it. So we have to figure it out that this clay is not that strong here because it hasn't been consolidated. So I end up with an SU. So when I figure out, using my SU over sigma prime I, in this case is given as 0.4, well, what's my sigma v prime? My sigma v prime, when I look at this picture, my sigma v prime at 6 is 0. So my SU is 0. At 12, it's only 286, which means my SU is only 114. So I had to come up with a different table of the SUs. And now when I do my calculation, now what happens? Well, the sand stays the same. Now, luckily, the sand stays the same. But the clay changes. And so I have to use these two strengths, those two SUs. So I put a 0 in and a 114. 0, 114. 0, 114. And my stresses are now, these are the stresses that I get in my clay. And notice Okay, let's look at these numbers. 600, 1032 versus 120, 552. So the excavation, so what am I saying? These are lower. These are lower. So when I built the wall by excavation, I have lower stresses on the wall. So that's because the soil is stronger because it's been consolidated with the sand when we excavate. When we build it by fill, this clay has not been consolidated by any sand. So that means I get a higher active, and then the passive is now lower because the clay is weaker. So I've got 0,888 for that situation, and then over here I've got 480, 1360. Well, that means that the passive is good. I want a big passive. Passive helps me out. So passive is good, active is bad. I don't want a high active. I want a low active and big passive. But this gives me a high active and low passive. So this situation is much more unstable. I get a completely different result for that situation. Now, if I do the wall for the drain condition, t equals infinity condition, so same wall, but now suppose I want it at t equals infinity, not t equals 0 plus. Well, now what do? Now I've got to use my drained equation for active and passive. So the sand stays the same, so I don't have to worry about the sand. But in the clay, I now need to fill out all my different columns here and do it like I did the sand. So now what do? I get my U's. You can all get U from the water table. And then sigma V prime is sigma V minus U. But then my sigma H prime, how do I get that? That comes from this equation, and that comes from that equation. You can plug in those values. And so I get my sigma H prime, and then, these are going to be sigma H is equal to sigma H prime plus U. So that is how I get the results at the t equals infinity situation. So, okay. This is, of course, you need to, So these are intermediate calculations. You can look at those. And here's a sample calculation for the 294. The other ones are similar. So take a look at that. You can pause the video here and look at how these numbers came about. We're just applying these two equations. We're just plugging into those expressions there. Now, all right. Let's see. Yeah, so this is just what I said prior